Let's start today with talking about the symmetry of the electric field. An important point is that the symmetry of the electric field must match the symmetry of the charge distribution that creates it. Put this in a different way. What do we mean about symmetry? We're talking about geometry here. If we have a sphere like that, it has a spherical symmetry. We can rotate it around the center. We can take a mirror image to it. Well, this is a different kind of symmetry. But anyway, we can rotate this around the center, and we won't see any change in the sphere because it's a perfect sphere. So, let's see. We also have so a point as a spherical symmetry as well. A line, there's a straight line. It can be, I'm not putting this way. All right. In physics, in geometry, when we talk about symmetry, we mean that how can we move the object in a way that, or change the object in some way that doesn't change the result. For example, let's take a triangle. There. I've made this an isosceles triangle in this case. Now, if I take a line bisecting, cutting it right down the middle, then I could take this triangle and I could flip it. I could take the mirror image of the triangle. And what I get back is the same thing I started with. So this isosceles triangle has a reflection symmetry, we would say. Let's see. If I have a cylinder, like this, I can rotate it around its axis. So it has an axial symmetry here. It looks the same if I rotate it a bit or back or whatever. It still takes up the same place. If I have an infinitely long cylinder with no edge, with no ends, then I can shift it left or right, and I haven't made any change either because there's no edge. If I were to take this finite length cylinder and shift it left y a bit, then it looks different when I come back because it's in a different place now. Okay, so when I say that the symmetry of the electric field's shape has to match the symmetry of the charge that creates it, I mean that, well, let's see, I'm still going a little too far ahead. What are we even talking about here? If I have a point charge right there, we already know that its electric field points out evenly in all directions. And out of the board and into the board as well. Now, if I were to, well, let's see, we call that a spherical symmetry. So I could draw a sphere surrounding this here, and you would see the electric field lines point from the center of the charge through the surface of this imaginary sphere, and they act as radius lines. So they have the one coordinate, the one dimension that really matters for the sphere. If you have a point of charge, those field lines are going out like this here. Okay. by looking at the symmetry, we could apply some of the rules that I told you about electric field lines, especially the fact that they can't cross. If we apply symmetry and the fact that the lines can't cross and that they are emitted from positive charges and they land on negative charges, we could draw the electric field shape qualitatively from knowing those facts. If I have a charge inside here, I'm going to draw a sphere centered on that charge, and I would know that the electric field lines must come out perpendicular to the surface of this imaginary sphere at every point. Because they can't cross, for one thing. So I couldn't have one field line here cross another one like that. The electric field can't go in two different directions at once, at the single point. So they can't cross, so that prevents that. Well, what if I had, couldn't I have the electric field up here bend upwards, and the electric field down here bend downwards, and really have not much in the middle? Could that happen? Now here's where the symmetry comes in. What is different about this side than this side? If I were to rotate this sphere and all the lines with it, I shouldn't see any difference. The charge that creates it has a spherical symmetry, and so the field lines coming out have to. Otherwise, I would be saying that there's something different about this patch here than that patch here. And if I were to rotate this up, why would they then be parting out sideways if everything has this, the charge has a spherical symmetry? And so what I can conclude is then that the lines have to radiate out in straight lines away from a point charge. What about a charge on a wire, an infinite wire? That has a cylindrical symmetry, where the field lines here have to come out at right angles to the surface of this imaginary cylinder I've drawn around it. This is supposed to be down below, and that's coming out of the board there. And that's on the back side there. And then, of course, up and to the right, from these points here, and so on. Because if they didn't, then there would be something special about this little patch of the wire than there was about that patch. But if it's an infinite wire that's the same everywhere, then the field lines, there's nothing special about this segment that's different about that segment over there. So they have to come out that way. And if I have an infinite plane of charge, uniformly distributed, the field lines must come off of it as parallel lines with a planar symmetry, P-L-A-N-A-R. Or they do the same thing going down the bottom side of it. So there's a mirror symmetry, and also if it's an infinite plane, then this continues on forever this way. If it is not an infinite plane, if it's a finite one, then I am going to see that there are going to be edge effects. Field lines coming off here are going to bend out away, because there is an end to what that symmetry is like. There's a difference at this edge and at that edge and at this edge and at that edge, and so on. Okay, so the symmetry of the electric field has to match the symmetry of the charge that creates it. Now we're going to use that as we go. All right, electric flux. Electric flux we're going to use the Greek letter capital Phi, P-H-I, and a subscript E will sometimes be put on there to stand for electric, and that's because later on we'll find that there is a magnetic flux as well. For the moment, though, this is the only kind of flux that we're dealing with, and so you won't always need to put that little distinguishing E under it. The flux is effectively, it is sort of like the number of electric field lines that pierce through a surface. So, if I've got a plane surface here, and I've got an electric field that goes past it, and then some of these go through it, like this. The flux is proportional to the number of field lines that go through this surface. So the area of the surface is important, of course. We're going to get to the mathematics of it in just a moment. But a basic idea is that you know that field lines are emitted. They move away from positive charges, and they move towards negative charges. Not that you have to have both, but I'm just drawing some over here. Okay. So we're going to use, in order to measure what's going on with the charge and to tell what's happening with the field, we're going to make use of these imaginary surfaces drawn out in space, surrounding charges or surrounding some region of space we want to measure things in. These surfaces are called Gaussian surfaces, because Carl Friedrich Gauss had come up with the idea of doing this. This Gaussian surface has, let's calculate the flux through the surface, and we're going to use that to relate it to the charge that creates the flux and to the electric field that goes through it there. Okay. I think I'm going to skip over much of the material in section 2 here because I'm going to go over it in more detail and show you why it works in section 3. Okay. So let's take a look at the electric flux going through some surface. Let me start off with a rectangular plane surface of area A, and we have an electric field. Let me start off with it being perpendicular to that surface. So here's our electric field, E, and there's A. Now, the electric field is coming through it like that. The flux in this case, in this very simple, specific case, for an area perpendicular to the, I shouldn't put it that way. We're going to change around directions. For an area, I'm going to say it. For an area where the surface is perpendicular to a constant uniform electric field, the flux would be equal to the electric field times the area. Only in this case, mind you. So it's field times area in basic units. And so it's going to have units of field times area. But the key thing that we've got to keep in mind as we do any calculation is the electric field and the area and the surface that it goes through might not be perpendicular like this. Usually they won't be. So what happens if you have a surface that is tilted? Now in this case, all right, here, I'm going to make the assumption that we have a uniform electric field and a flat surface. in that case then, the flux of the lines going through this is going to be different. It's going to be smaller than when the surface is face on. And that's because we have the electric field, in a sense, sees a smaller area if it's tilted. Let's imagine that, I'm just going to draw one of these lines here. There's E. If I draw a vertical line here, now that this electric field, I'm going to imagine, is horizontal. If I draw a vertical line, and the surface is, this is supposed to be a three-dimensional view, if the surface is tilted away from vertical by an angle theta, then a perpendicular line to the surface, we'll call it the normal line, is tilted at the same angle theta with respect to the field direction. And I think you can see that that would be the case then. Now, if I take a look at this, let's see here. Let's say that this area, this rectangle, has a length, a width x, and this other dimension here, y. And so the area is just equal to length times width, or whatever I'm calling those two dimensions. What area does the electric field see as it's moving forward? What area is actually covered by the electric field? It's going to be x long, but it's not going to be y height anymore. It's going to be something smaller than that. Let me see here. I'm going to draw dashed lines there, trying to keep the sense of perspective going on. Okay. Now, this is a right triangle here. The hypotenuse is y. I want to find out what's the area of this vertically hanging rectangle that's vertical. When the rectangle that's my real surface is now at an angle theta from vertical. Okay, so what's that rectangle there? What is its area? Well, it's going to have a length of x there, from here to here, but the height is going to be y cosine theta. And that's because we've got the cosine of theta is equal to the, let's see, so cotor, so adjacent over the hypotenuse. So that is the adjacent side over y. So y cosine theta is equal to the adjacent side, which is that side there. So that area then of that vertically hanging rectangle is x times y cosine theta, which is just a cosine theta, because a is x times y. Okay, that means that if the surface were hanging vertically, there's the electric field, and let's see, I need to name this vector here. Let's call this the area vector. The area vector, which will be capital A for area and a vector symbol, it has a magnitude equal to the area of the surface that I've shaded here. But it will have a direction that is normal, perpendicular to that surface. That's going to be really useful then for describing the shape of the surface that changes, it bends, and moves around and so on. Okay, so if the electric field hits the surface face on, and these are parallel, theta equals 0 degrees, And let's see here. Let's see, I'll put it, my electric flux is going to be EA cosine theta. E is the electric field. A cosine theta is the area of the surface that it sees. And since theta is 0 degrees, EA cosine of 0 degrees, that's 1. And in the perpendicular case, that flux is just EA. What about if we swing that surface up a bit? There's the area vector. There's the electric field. And let's say this angle is 30 degrees. Okay? Then the flux is EA cosine of 30 degrees. That's supposed to be a brace there. That's 0.866. So that's 0.866 times EA. So you see that the amount, the flux through the surface gets smaller as the angle between those increases. For that matter, I could have the surface be edge on. Now the angle between them is 90 degrees. So the electric flux is EA cosine of 90 degrees, which is 0. So if the electric field slices right along the edge of the surface here, not piercing into it or out of it, then the flux through the surface is 0 because none of the lines cross it. So now you can see that this flux, the electric flux, is proportional to the number of electric field lines that go all the way through the surface. And if you turn the surface in some way, or if you turn the electric field in a way so that fewer of them get to go through it, then the flux goes down. Okay. By the way, the book explains this somewhat differently as the amount of the perpendicular component of the electric field times the area. I prefer to look at it, or it's easier to derive, I think, if you look at it as the electric field times the fraction of the area that field sees. So, let me put this together. Let's see. In the case of a flat surface and a uniform field, then what we get is the flux is equal to EA cosine of theta, the angle between them. But look, there's a better way we can do this, a more compact way. If you remember, if we have two vectors, and let's just say vector 1 and vector 2, and an angle between them, theta, then the dot product of those two vectors is a scalar. It's just a number, a magnitude. The magnitude of that dot product is magnitude of vector 1 times magnitude of vector 2 times the cosine of the angle between them. And look what we've got here. We've got two vectors, their magnitudes multiplied times the cosine of the angle between them. So let me just rewrite this as E dot A. Both of these are identical. This lower one, though, is going to be more useful to us because it will allow us to generalize for when we don't have a uniform electric field in a flat surface. But for right now, these two equations hold just for uniform electric field in a flat surface. Now, what about when we have a curved surface or a non-uniform electric field? Let's start with this bit then. So flux for the uniform case is equal to E dot A. So what we're going to do is we're going to break our more complicated surface up. Let's imagine that we've got something like this. All right, some kind of a scoop-shaped surface. And we've got an electric field that's splaying out in all directions through this here, although obeying the rules, of course. What I will do is I'll take the uniform case and I'll apply it to every little infinitesimal bit of this surface. Let me draw a grid on here to help us imagine that. There. You know, my artistic skills aren't as bad as I thought. So I'll take, and I'll draw the electric field. Let's imagine the electric field is kind of coming away from, maybe it's a point charge, but it's diverging away from that there. And I'm going to take a look at it through several of these places here. There. Like that. I'm trying not to make them look perpendicular in every case. I want them to have some kind of an angle in general. Okay, so those blue lines are my electric field lines. Now, the total area is capital A. So all of my little bits of area, well, if we were in an algebra-based course, we'd talk about that delta A, a fragment of the total area. We're more sophisticated than that. We'll talk about dA, the differential little bit of area. In this case, it's not really a difference between this amount and that amount so much as it is a component piece, an infinitely small component piece. The reason we still can talk about it being like a difference is that it's the difference between what was over here and what is over on this side. This is the difference between those two parts. So we use the same language there. So this little bit here, that I'm shading in, has area dA, and I'm going to draw its area vector. Perpendicular, intended to be perpendicular, forgive me. Perpendicular to that surface. And here's the electric field vector there through that little bit of surface, that bit dA with normal direction there. I'll draw in a right angle just to make it look like it really is normal. Okay, and they've got an angle between them, theta there. All right. Now, the key is, since we can only apply this rule when we have a uniform field and a flat surface. If we get down to infinitely small sections, every little infinitely small bit, if we get small enough, it is flat. And then the curve is because the next piece is at a slightly different angle, but it's basically flat, and so on like that. So this is taking the limits and so on. So in this case then, I want to add up the total flux. The total flux is the sum of the little bits of flux, d flux, d phi, through each one of these pieces of it. So what I'm going to do is I'm going to say that the total flux, phi sub e, is equal to d phi sub, well, I'm going to drop the subscript e for now because we know it's electric, and I need to use the subscript space to write in piece number 1, piece number 2, and so on. D phi 1 plus d phi 2 plus d phi 3 plus so on like that, because fluxes add, just like charges add, forces add, vectors add, and so on. Okay. And so what is d phi? Well, that is the infinitely small bit of flux that goes through this infinitely small bit of area and with that electric field there. So d phi is going to be equal to the electric field E dotted with the area vector for that infinitely small bit dA. And really, because I've got an infinite number of these that I'm summing up, well, it's an integral. Each one is infinitely small. So the total flux is equal to the integral over the surface. Explain that in a minute. I won't always write surface underneath these because it will be understood. Of E dot dA. So for every little bit of these, I calculate the flux of that infinitely small bit, and I go to the next piece and so on like that. All right, and this is the important result here. What is a surface integral? Well, a surface integral is, in principle, it'll be a three-dimensional integral. You've handled one-dimensional integrals. Maybe you've had a case with a two-dimensional integral before. And this is, in principle, a three-dimensional integral. Let me make a note here that the integral of dA itself is A. You add up all the little pieces of the surface, you get the total surface area. And of course, well, the direction there. I'm going to remove, this is true without the vector symbol, certainly. I'm going to remove the vector symbol because if it's a curved surface, which way does A point? Well, it doesn't really, does it? But this is true even, maybe especially, without having that vector symbol. Okay. So, if we had to calculate these mathematically, I mean, with equations and so on, surface integrals can get pretty complicated in principle. They don't always have to be, and we're going to take only the simplest cases. As the book notes, we're going to do it so that all the surface integrals we have to do are going to come out to be either 0 or something that's blatantly easy that they say you could do in your head, and I think you could. But what is it? In principle, it would be an integral over x, y, and z, or r, theta, and phi, or whatever your other three coordinates are. So it would be something like an integral over x dx, an integral over y dy, and an integral over z dz times all the other, whatever equation you have. There are equations of functions, I should say, for the shape of some surface. And you put that function in there and you integrate. You integrate dx, dy, and dz. The result of one integral goes into the input of the next integral, and so on. And anything that's not dependent on z, you can pull out into the y one. If it's not dependent on y, you can pull it into the x one. And if it's not dependent on x, you can put it to the outside of the whole thing. We won't have to do that. Okay. So, don't think of an integral as as some kind of a formula for how you transform, like the integral of x squared is 1/3 x cubed, for example. Don't think of it as that. Think of it as the integral is adding up. And for the surface integral, you're adding up things at every point on the surface. How we do that is what we're going to get to. Okay, let's see here. A thing to note, there's no vector symbol on phi. By the way, I will not always write the serifs on the top and bottom of phi. I'm doing that to emphasize that it's the capital phi, not a lowercase phi. Lowercase phi is often used as a marker for an angle, although I'm not going to do it here to avoid confusion. But it is always capitalized whether I put the serifs on it or not in this case. These are both vectors, but this is not. This is scalar. That's because the dot product is a scalar product. You get out a number, 17 or 38 meters squared or whatever it happens to be, but there's no direction, there's no vector to it. Okay. Let me cover two simple cases of doing a surface integral. If you happen to have E and A both constant, Now, if E is constant, that means it's a uniform electric field. If A is constant, it means it's a flat surface. The normal vector is the same everywhere. In that case, then you've got E dot dA. I should have said dA is constant, not A. Because dA is the little bit that is in different places. Now, if I do the dot product then I've got integral of E cosine theta dA. So I've got a situation with a plane surface, and I've got an electric field sticking out at some angle there, and I've got dA is the same in every spot, something like that. So there's a constant angle between the two components. They've got the same magnitude everywhere. E cosine theta doesn't change, E doesn't change. I pull them outside the integral. E cosine theta integral of dA. Yes, it's a surface integral, I'm just not writing that. And the integral of dA is A. And I get E A cosine theta, just like I did back here for the uniform case, because it is uniform. So that it's good. If I take the general case, I get back what I got in that specific case. Now, using this fact, what if it's uniform and E is perpendicular to dA everywhere? For that matter, it doesn't even have to be uniform, but if it's perpendicular to dA everywhere. Now, not perpendicular to the surface. dA sticks up perpendicular to the surface. So if E is perpendicular to that, it's parallel to the surface. So, there's my surface, and, oh boy, how to make it not look like it's sticking up. Right, like that. And here are my little area vectors there, E and dA in those cases, and they have right angles between them. Now, in this case, phi E equals the surface integral of E dot dA. That means E cosine of 0 degrees, of 90 degrees times dA. Cosine of 90 is 0, so the flux is 0. No lines go into or out of that surface. And for that matter, and this, by the way, happens, this would happen as well, even if you have a diverging field and a curved surface. Take a look at the case of a sphere. Now, I better not do that. I'll do the next case, which takes care of a divergent. If I have E parallel to dA, now if I have a little rectangular patch here, and there's dA, I'll just draw one of them, and there's E, I'll just draw one of it, then flux is the integral of E dot dA. That's the integral of E cosine theta dA. And if it's uniform and so on, cosine theta, that's cosine of 0 degrees, which is 1. So I get E times 1 times the integral of dA. Integral of dA is A. I get dA, which is what I got in the uniform case. But this is nice because this is even true with curved surfaces. So is this, by the way. But let's imagine I've got that little positive charge in the center of the sphere, and I've got my E field coming out perpendicular to the sphere at every point. Okay? dA is also perpendicular to the sphere at every point because it has to be normal to the surface. So there's dA here, but here's E and here's dA. In this case, then, I can find the one of these more complicated cases, if I choose a Gaussian surface that matches the symmetry of my charge, as I said before, so if I choose a Gaussian surface in order to match the symmetry, the field lines have to have the symmetry of the charge. But if I can choose any Gaussian surface I want to and integrate over that and find a flux to it. And if I choose one that very cleverly mimics the symmetry of the charge and therefore the field lines, I get these perpendicular lines there, and things come away very nicely. Okay. You know, an integral is adding up things. We just passed the birthday of Wilhelm Gottfried Leibniz. I think I said his first name right. Who's one of the, he and Isaac Newton came up with calculus, really independently of each other, although they kept arguing over who did it first. I think Newton did it first, but Leibniz did it a simpler way, or especially a simpler notation. And this, here with the D for differential and the long S for the integral symbol, those are his notations. So what is the integral? It's a sum. It's the letter S. It stands for sum, adding up of things. And let's keep that in mind, because it means that you can break up an integral into a sum of other integrals, each one, as long as they're not overlapping, each one taking a different section of your surface. What if I have some surface which is like that? Maybe I've got some flux going, some electric field coming over this way. And they pierce through here, but they're not going to pierce through there. But this is just a flat sheet, a flat sheet, a flat sheet there. Now when I do this integral, it would be easiest in this case to break it into the integral over this surface plus the integral over that one plus the integral over that one. Each one of those then has a nice, a simple equation, simple function for describing the surface in each one of those cases, and they're very different from each other. And I would also, in this case, wind up getting a uniform E field of a constant angle away from the surface. Okay, so if I want to do that, then I can write that the total flux is equal to the flux through surface 1 plus the flux through surface 2 plus the flux through all these other surfaces, which means integral of E dot dA total is equal to the integral of E dot dA1, that's for surface 1, plus the integral of E dot dA2, that's for surface 2, plus, and I go on down the list like that. So break these up into surface integrals over well-defined regions that you can handle at a single interval. And of course, you know that this flux is going to be 0, that flux will be 0, and this will be EA for surface 2. Okay. Now, that brings me to handling, if we can add up different sections of the surface. Well, we can make a box, we can make a sphere, a cylinder, a can, or something like that. We can completely enclose a region of space. What's called a closed surface. So, for example, I can take that sphere there, that's a closed surface. Or I could take a box, like that. A couple of things that are ambiguous. If I'm doing a surface integral over a complete surface that doesn't leave any gaps here, if I were putting this in terms of x, y, and z, or r, theta, phi variables, coordinates, then there would be some ambiguity on that, on this interval, because the limits where I start at the bottom here and where I end at the top are the same point. If I start here, or maybe along that line, and I integrate here, 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 there, and there, and I come back, I've got to finish up where I started. But that's sort of like, if I had said, well, from x equals a up to x equals a, normally that would look like you start and finish in the same spot, you haven't gone anywhere. Therefore, the interval, if there's no change in dx or dA in this case, the total interval will be 0. You haven't integrated over any coordinate. You just started and stopped at the same point. So what we want to do then is we put this little loop symbol around, called a loop integral, or a closed surface integral, because we're in multiple dimensions here. That symbol tells us that we're going over a complete loop or over a complete surface. And that way we don't mistakenly think that we're not really doing the integral at all. Okay, so that's a bit of notation. Okay. One other point. When I was talking about a single surface like this, and I said, here's the E field. Actually, I should draw it in an angle. Let's make the E field be going down like that a little bit. And then here's dA. Isn't there some ambiguity? This is just a postage stamp shape here, so it's a rectangle, it's flat. Why wouldn't I have said that dA points out that way? And so you're going to get a very different angle if you go from between those there than if you do between these here, right? Which way does dA point? Well, if I only had that one sheet there, I actually would have to specify it. And there are cases where it could be one way or another. But if I'm going around a closed surface, there is no ambiguity. I'm telling you that in each case, if there's a closed surface, dA will always point away from the surface, never inwards, always outwards. I'm not putting subscripts on each of these. Probably I should, because there are 6 surfaces here, but I think we'll see. Oh, and for this matter, on a smooth surface like the sphere here, dA is always pointing outwards as well. And so on like that. Now, this is interesting because, keep in mind, for a, let's say for a uniform, and it doesn't have to be uniform. I'll take the differential form. Let's see, E dot dA. So E cosine theta times dA, without the vector symbols. If you've got let's take a uniform electric field going through this rectangular box here, this cubic box. So let's see. I'll just draw a single one here. Coming in, there's E coming in, and here's E coming back out, and of course it grazes along the top here, and it grazes along the bottom there, and it grazes along each of these sides, and that side as well. What is the total flux through this box? What we can do, and I'm going to say that A is the same area for each face, so that's a cube. A1, A2, A3, A4, A5, and A6 are all the same. Flux, R So I've got the flux on side 1 plus the flux on side 2 plus the flux on side 3, and so on like that. Fluxes added for each of those different surfaces. Integral of E dot dA, I should have subscripted EA1 plus integral of E dot dA2 plus so on like that. By the way, this is not, there's 1, there's 2, 3, 4. Actually, I should, let's put the one on the left is 1, the one over here is 2, and these others will be 3, 4, 5, and 6. This is not a closed surface. This is only one pane of that, so I'm not putting that symbol. Now, E dot dA1, I've got E cosine theta 1, cosine of 180 degrees times dA, and that is -1. So I get out negative E A. I'll just say for that's surface 1 has got area A. Plus integral of E cosine 0 degrees dA. 0 is positive 1. So I've got plus EA. So the flux inward here is negative, and the flux outward there is positive. And those two cancel out exactly. The flux along these other faces here is 0 because it's perpendicular. So the net flux through of an electric field through a closed surface, I should say an external electric field. There are no charges inside this. The net flux through that closed surface is 0. As long as there is no charge, either positive or negative, inside the surface, because rays emit from that or all in on it, then whatever comes in has to go out. And then the total flux winds up being 0. The same would be true for a sphere. Proving it would be more complicated. So on like that. The angles are all different. But if we remember that the flux is basically counting up the number of field lines that, the net number of field lines coming out of that surface. Okay, you subtract the ones going in, you add the ones coming out. Then, if it goes in and comes out, the net is 0 for all of those. You will only have a net flux through a closed surface if there is charge inside, a net charge inside. And when I say that it's sort of like counting the number of field lines, it is, except you've got some units you've got to multiply that by. So it's not just a number like 17 field lines, it's that times and then some densities and other factors and so on. Okay. Now we're going to make this into a really useful form with what's called Gauss's Law. Again, with, if I remember his name correctly, Carl Friedrich Gauss. He had found out that the electric flux through a closed surface, the closed surface interval, E dot dA, that flux is equal to the net charge enclosed within the surface divided by the permittivity constant, epsilon naught. Okay. Now this means that if you have an equal number of positive and negative charges, you still have no net charge. If you have 2 protons and 2 electrons, the net charge inside that is 0, and therefore there would be no net flux. It's only if you have an excess of one kind or the other. Okay, an example, and a proof of this in the simplest possible case. If I have a positive charge here, and I take what surface do I want? Well, it's useful to use Gauss's law if I take one that matches the symmetry of the charge. That's the kind of surface I want to draw, I should say. So I'll make it be a sphere of radius r, arbitrary radius, centered on that charge. Now I know that the field lines must be coming out normal to the surface everywhere. Okay. And dA is going to be normal everywhere, as it must be, by definition. And so on like that. So I've got charge Q, lowercase q inside. It's a point charge, so I'm using lowercase q. So in this case, flux is equal to E dot dA, closed surface integral. Now, because E is parallel to dA everywhere, so it's normal to the surface everywhere, then the dot product, I've got cosine of 0 degrees, which is 1, and I wind up with integral of E dA. E is constant, I can move it outside. Now I've got the surface integral over dA, which is just A. So my flux, in this case, is EA. Great. What is EA? What is E? What is A? Let me make a little more room here. The electric field of a point charge is given by Coulomb's law. 1 over 4 pi epsilon naught times Q over R squared. All I want is the magnitude, not the vector here. Times, and what's the area of a surface area of a sphere? It is 4 pi R squared. Now look here. 4 pi, 4 pi. R squared, and I'm left with Q squared, Q over epsilon naught, which is just what I said up there. The net charge is just Q. It's the only charge for that matter. Okay, but fine. This works when we've got a point charge and we have it inside a concentric circle. But take a look. This applies in other cases, because you notice that the radius of that sphere, it's a concentric sphere, the radius of that sphere doesn't appear here. It doesn't matter how big I made the sphere, the same total number of field lines pierce through the sphere no matter how big it is, because they're going out in a radially, in a spherically symmetric shape. This allows me to do something else. What if I didn't center the sphere on the charge? What I could do is I could break this enclosing surface into any other shape I wanted to, where the shape could be, there's my charge. If I want to do it in some big kind of a oval like this, each section of this oval, I'll take this as a cross section. I can take a little section there and infinitesimally approximate that little bit as an arc, a section of a sphere that is tangent to this at that point. And there, and so on like this. Well, not tangent to this. It goes out and approximates the shape of that curve there. Okay. When I do that then, and each one of these is of a different radius, which doesn't matter. but each one of these is a section of a sphere centered on that charge there. And so I know I'm going to get that out of it, and I know that I can break up a surface integral into an infinite number, or into a sum of other surface integrals that each take a section of it. And here, then, I just approximate the shape with a bunch of little segments of spheres, and so I come up with the same thing. Whether it's off-center, whether it's centered, whether it's a different shape other than a sphere, it winds up applying to everything. Okay, now this is about the net charge of a closed inside in the closed surface. So what about the charge, what about the case where you've got charge outside the surface? If I've got some little charge here, and I've got the dumbest choice, looks like modern art from the 1930s or something. If this is my Gaussian surface here, and there's no charge inside that surface, take a look what happens to each of the field lines. It goes in, comes out. Goes in again, comes out. What about when it goes over here? In, out, in, out, and so on like that. And you see, every time a field line goes in, it's going against dA. Now, dA at that point points in the negative direction relative to the field. So you've got a negative sign on that little bit of flux going in. But every time it comes out, dA is pointing in the positive direction relative to the field, and now you're adding that same amount back in, and then negative and positive, and all of these cancel each other out for a single way because it doesn't end inside the surface, and it doesn't begin inside the surface. The same thing here, and the same thing there, and so on. So, since the same number of lines enter the surface as leave it, the net flux is 0. Okay, that's an important point. Now, we've got, I think I'm going to do 2 examples on applying Gauss's law. Let's see, in an infinite or a long charged wire, I'll do first. Okay. The book goes over these, but I'll explain them myself. If I have a long wire, then let's remember, long, maybe infinitely long, but what Gaussian surface should I use to look at, I'm putting, by the way, positive charges along this wire. You could figure, if you didn't already know, we derived the electric field from a long wire. The reason I'm even doing this is that one thing that you can use Gauss's law for is to find out the form of the electric field from some distribution of charge. We can use it even to derive Coulomb's law itself, but let's take a look at something more complicated. Let's take a look at that infinitely long wire we did before. Pretend we didn't know it. Now, we didn't derive it. So far, we derived Gauss's law using Coulomb's law, but we derived the infinite wire electric field earlier using the superposition of all the infinite number of infinitesimal charges. What if we don't do that? What if we just take Gauss's law here? We can do it more simply. First of all, what is going to be the shape of the electric field lines? You need to know that. from the symmetry of this, and we know that they can't cross, they have to start on positive charges and end on negative ones. We know that they're going to be, they're going to have a cylindrical symmetry. Okay? So if they're extending radially outward from the wire and in parallel lines from that then the symmetry we want to apply is a cylinder. Now I've drawn edges to it here, and we will put in, since we need to do this over a finite space and then extend it, I'll make this be a cylinder of length capital L. Like that. Okay. And it'll have, we can have a radius R. I guess I do need to draw the radius in. There's R. Okay. So we chose a Gaussian surface that matches the symmetry of the field lines. That was the importance of going over the symmetry. Now, total flux is going to be equal to the flux through each part of this surface. So, I want to have the wall of the cylinder and the two end circles. Now, let me see how the book writes this out here. So, let's say here, left disk plus the right disk plus the cylinder wall. That's the curved surface there. Okay, each one of these is going to be E dot dA. And they're going to be little bits Q, charge Q along here. From symmetry, we're going to know that the none of the field, since the field lines have to go out straight away from the wire, they can't go at some angle to it, then none of them pierce through the left or the right discs. And we're left with just the wall of that cylinder. Now, because of that same symmetry, E and dA are parallel to each other here. Integral over the wall. These are parallel. So I've got integral of E cosine of 0 degrees dA. And that's just 1. I can move the constant E outside of that then, and I've got E times the integral dA of the wall, and that's just the area of that wall. The area of that wall is it's got a length L and a radius R. E times, let's see, the circumference of that circle is 2 pi r times the length, so I get 2 pi r L. Okay, so the flux through that cylinder is equal to E 2 pi r L. Great, but what I would like to get out here, I want to use Gauss's law, and I want to find the electric field. So I want to solve for this. So let's take this. So we've gotten, let's see, we'll apply, we've calculated the flux directly. Now we apply Gauss's law. So we also know that the flux is equal to Q over epsilon. Epsilon naught there. What is that charge? Well, if we have an infinitely long wire, there's an infinite amount of charge. So we use the flux density. It's a linear, one-dimensional density. which is equal to charge per unit length. Therefore, Q is equal to lambda L. Now, that's from Gauss's law here. This is from calculating the flux, this part of it here. Now we set these two equal to each other. So, the electric field times 2 pi r L is equal to lambda L over epsilon naught. The length of this segment that we consider falls out. Divide both sides by 2 pi r, and I've got lambda over 2 pi epsilon naught r. And if you look, you will find that that's the same that we already found from the infinite wire case. But we did it much more simply applying Gauss's law. Do the surface integrals, set it up in such a way that some of these go to 0 and the other part has a perpendicular, the field lines are perpendicular to the surface, therefore parallel to dA, which makes that easy. Set that equal to the amount of enclosed charge over epsilon naught. If you have an infinite amount of that, then you could put it in terms of the charge density. In order to get the vector, we should know then that from the symmetry, that's how we have to know the vector. So we have to know what that charge distribution is actually like. And so in this case, from symmetry, we know it has to point radially away from the wire, and so we can get the vector form of this there with an R unit vector. Okay, and last I'm going to do the electric field of an infinite sheet of charge, which is even easier. Since we've got an infinite amount, I'm going to go on ahead and talk about the surface density, which is going to be eta, which is equal to Q over the total area, capital A. Okay. Now, I'm only drawing a segment of this infinite plane, but we've got positive charges uniform across the surface here, with the plus signs. From symmetry, I know that the field lines must go out perpendicular to the surface. Okay? Now, what I'm going to do, following the book, is I'm going to enclose these field lines inside cylinder segments. And it's kind of hard to draw that on the other side, but there. All right. And it's going to have a total length, that cylinder will have total length capital L, and the, let's see, faces of area A. So the face of this cylinder has area A, and same there's an area A over here. Now keep in mind that dA points outward here to the right, and it points to the left over here. That's going to be important. Okay. So first we calculate the integral for the flux. E dot dA. We break that into the integral over the wall, E dot dA, plus the integral over the left cap, E dot dA, plus the integral over the right cap. Now in this case, the field lines are coming parallel to the wall, so there's no flux through the wall. For the left and the right ones here, both of these, the field lines are parallel to dA, but it's positive in both the left and the right cases because the field is going to the left when the surface goes to the left and to the right when the surface goes to the right. The ends have area A on them. So for the left, I've got field that way, dA that way, so it's positive. E times A plus E times A on the right. So that's E times 2A, so 2E times, what's the area of those? That is pi, let's see here, what is pi r squared? Oh, yeah. Of course, this is an arbitrary cylinder of an arbitrary radius, but it encloses an amount of charge here, where if eta equals Q over A, then A equals Q over eta. I'll put that in here and here. Okay. Now I use Gauss's law's conclusion that that same flux is equal to, so that's flux, is also equal to the enclosed charge over epsilon naught. I put these two together. 2e Q over eta is equal to Q enclosed, which will just be that Q there, over epsilon naught. Good. The Q's drop out. I want to solve for the electric field. And I'm going to wind up getting, let's see here. I think I've got, no, that's correct. Good. So I'm going to have eta over 2 epsilon naught. There. And that came up much more simply than doing it the hard way using superposition. Now, one of the problems with using Gauss's law this way is that it's easy when you have these symmetries, geometric symmetries, but we generally won't. And so you could wind up with some really difficult integrals, and then it might not be simpler than doing it the way we did in the previous chapter with using superposition. In these cases, though, it is. All right, now let's take a look at what happens when we have not just charge, but we have conductors. And we apply Gauss's law to them. All right. Again, a conductor, very often a metal, but there are other kinds of conductors as well, like water with a lot of minerals dissolved in it, salts and things. What's electrostatic equilibrium? That is when the charges are static, they're not moving. So, if they're not moving, that means there's no current. Current is a moving charge. And that's going to be an important point. A conclusion from this is, if there are no charges moving through the in the conductor, then we must have the electric field equal to 0 everywhere inside the conductor, in the material of the conductor itself. That is a very important conclusion. Now, the reason for this is that if there was not an electric field, if there was an electric field in the material of the conductor, remember the electrons are free to move through the metal. I'm going to just say that it's a metal here. The electrons are free to move through the metal. Secondly, an electric field produces a force on a charge. So, if there is an electric field in the material of the conductor, it would be pushing on the charges there. But if they're moving, and if it's pushing on them, they're moving. If they're moving, the charges are not static, they're not stationary, which was the condition that we talked about to begin with. So it would violate the condition. So as long as we know that the charges aren't moving, then we have to have no electric field in the conducting material. Now, because of that, if the electric field is zero in the conductor, then we apply the equation for the flux, the electric flux. It's equal to integral of E dot dA. Okay? If E is zero, then the flux is zero. Now, what surface are we talking about? What Gaussian surface? If we put a Gaussian surface that is just inside the conductor's exterior surface. There's some random shaped conductor, cross-section of it. And if I make my Gaussian surface be just inside that, there's a reason for saying just inside, because I've said that the electric field is zero inside the conductor, not outside necessarily. So if my Gaussian surface could be some complex shape, but it matches the shape of our conductor, and it's just inside the skin there, the flux through that Gaussian surface is zero. Now, because Gauss's law says that that's equal to the charge enclosed within the surface divided by epsilon naught, you put these two things together, therefore, the charge enclosed within this Gaussian surface, shown in red, is also equal to zero, meaning there is no net charge within a conductor that is in electrostatic equilibrium. Interesting. No net charge in the conducting material. That means that, now, by the way, I'm assuming that this is a solid conductor, no holes in it, no bubbles or anything. We'll get to that case in a moment. That means that all of the charge, any net charge that a conductor has, net charge, must be on the exterior surface. Sitting right on the outside edge. Okay. Another thing. And by the way, it doesn't have to have a net charge, but if it does, it must be on the exterior surface. Now another thing, all electric field lines, whenever they touch a conducting surface, must be perpendicular to the surface. Let's see here. You could get some complicated shape like this, with it crowding together, but whenever it comes off the surface, it has to be perpendicular at that point. It can bend later. Okay. At the surface, not, near it, it can be at a different angle. But at the surface, if an electric field line touches the surface, it has to be perpendicular to it for a conductor, not for an insulator. The reason for this is that if you had, let's see here, there's some surface. If you had an electric field that came off at an angle to the surface, then it would have a component of that field that would be, let's see, we can break that down into tangential and parallel components. Sorry, tangential, perpendicular and parallel components. If there is a component parallel to the surface, then the force exerted by that field line would accelerate the charge that's there. And if it accelerates the charge, then the charge moves, and then we don't have an electrostatic casing. So remember, charges will move if they have if they're in an electric field, and if they're able to move through the material. The charges in general are going to be stuck to the surface or stuck to the conductor, and therefore they don't easily move off the conductor. There are cases where that can happen, but they can move within it or along it. But if they can move along it, then if there's an electric field parallel to the surface, they'll move with it, and we no longer have electrostatics. One thing though, let's see here. The electric field at the surface is then equal to the surface charge density eta divided by epsilon naught, you tend to get that, times the normal vector up to the surface. So just like the case for one side of a sheet of charge. But the thing is that the charge density, eta, changes from one place to another over the surface. You can see that the field lines are getting, they're kind of getting dense over here and spread out over there, and so the charge is rearranged in a way that makes the field lines work properly. So the charge density varies from one place to another on the surface of a conductor, and it depends on the conductor's shape. We won't get to that yet. All right, the last thing, we've got three interesting little cases here, which we can do in a hand wave sort of a way. All right, let's say that we've got a bubble, I should say an empty bubble. We'll get to a field case in a moment. An empty bubble in a conductor. So if I've got a conductor there, and it's solid except for a little bubble inside it. Solid conductor except for that little bubble there. The question is going to be, is there any charge on the inside surface of the conductor surrounding the bubble? Because let's say that we've got some net charge on the outside surface, and we know that that can be the case. And I said that charge will rearrange itself so it's all moved to the outside edge. The electric field from each of these charges pushes them apart as they'll go there, but does it make any of them move to this surface here? And it turns out that there is no charge on this. If the bubble is truly empty, if there's no charge in that little air gap there inside the bubble, then there won't be any charge on the surface here. And to see why, let's say that we enclose the bubble inside a Gaussian surface, shading it to show you that that's three-dimensional. Now, we know that inside the material of the conductor, the electric field is zero everywhere. Now let's put a Gaussian surface surrounding the bubble and a bit of the conducting material right there. And we know that the flux within that Gaussian surface is going to be the surface integral of that Gaussian surface over E dot dA. Okay, now, if the electric field is zero everywhere here, and we know we have no charge inside the bubble, then that is zero, and the whole thing is zero. Flux is equal to zero. But we also know that from Gauss's law that the enclosed flux will be equal to the enclosed charge, sorry, the enclosed flux. The flux through that surface will be equal to the charge enclosed by the surface divided by epsilon naught. And if I put that in then, I get that there is no net charge within the Gaussian surface. Therefore, if there's no charge within that bubble itself, there has to be zero charge on that inside surface as well. So, for bubbles, empty bubbles inside a conducting material, there's no charge on that inner surface of the conducting material. Let's apply this then. We can use this fact to make what's called a Faraday cage. Let's say that I've got an external electric field. I'll draw it uniform for simplicity's sake right now. Now let's say that I put, if I put a hollow conductor in here, in this case I'll draw just a box. Now, I know from what I just derived that the electric field, and by the way, the field in here will also be zero inside the bubble. So E equals zero inside this metal. But how can that be when you have this external field? Well, you see, the charges will rearrange themselves. Where the electric field hits this, it has to be perpendicular. But look here. Oh, it's going to be perpendicular again. And then you would also get field lines up here that sort of bend like that. There's a smooth change. There, sort of like that. All the field lines have to hit the conductor perpendicularly. Now, if that's the case then I have to have negative charges here where the lines come in, and positive charges over here where the lines leave. And so the electric charges on the exterior surface of the conductor rearrange themselves. Even if it's electrically neutral, it polarizes the conductor. Positive charges over here, negative charges over here. And another way of looking at this is that even though there is an external electric field, you can see that then the electric charges here and here rearrange themselves in such a way that the field, if you could have fields inside the conductor, the field from that positive charge to that negative charge going the opposite way would exactly counteract the external electric field going this way. And so you wind up with zero field inside a hollow conductor, even though there is an external field out there. The usefulness of this is that radio waves, radio signals, are electromagnetic waves, so they're vibrations in the electric and magnetic fields. And you can block radio waves if you've got some sensitive instruments and you don't want them picking up these changes in the electric field. You can make the electric field in a room be zero. by lining it with metal. In practice, we can often get away with using a wire mesh, depending on the wavelength of the regulators. And that's called a Faraday cage. Finally, if we have a bubble in a conductor with charge Q inside it, let's see. So let's say that there is a charge inside the bubble itself, not on the surface of the bubble, but just floating there in the hull. Okay. In this case, then, if I take my Gaussian surface around that, the Gaussian surface, let's see here. The Gaussian surface encloses part of the conducting material, but I know that the flux through that Gaussian surface inside the conducting material has to be zero because the field inside the conductor must be zero. Therefore, since the flux must also be equal to the enclosed charge divided by epsilon naught, the total charge enclosed in the Gaussian surface must be zero. But if I know that there is a charge in the bubble part, that means that on the surface, the interior surface of the conductor, there must be an equal number of opposite charges, or equal amount of opposite charge. So if I have some amount of positive charge, then I must have an equal amount of negative charge on the interior surface. Now in that case then, if the conductor were neutral, then the fact that there's a net negative charge on the interior surface means there must be the same amount of positive charge on the exterior surface. And the neat little thing is then, that despite all this complex distribution of charge, if you take a Gaussian surface surrounding the whole thing, what's the net charge inside this Gaussian surface? That little piece right there is the only net charge. Because the amount of negative charge on the interior surface is equal to the amount of positive charge on the exterior surface, which add up to zero, leaving you only this. And then, Gauss's law would tell you that you know the number of field lines piercing through this larger Gaussian surface surrounding the whole conductor with the bubble, with the little charge inside it, is just as if there was only that little bit of charge and not the rest of that conductor. As far as the flux goes. All right, and that's the end of our lesson today.